gonna be this resistor plus so what I need to do is find out what the parallel impedance of that mess is. 200, 180, and 240. So I'll apply the 1/over method. What that works out to be, mistaken, is 192.7.
What is that first V up there?
Sorry,
What is that first V?
what's that first Z?
The
Total
NT.
impedance.
It's V1. Oh, yeah.
Total impedance.
That's not.
That's I.
No, I'm talking about V.
Right.
I'm talking about the first. I'm talking about the third volt. The third one up there. The voltage.
V100.
Okay. That's one. All right.
Because once you find the parallel voltage, that's the same as voltage across 200, 180, and 240.
And you said it should be 192?
I don't know, check me out.
Well, that's what I got, is 192.7.
That's what I got.
Let me check it out. Let me
But
check
I'm
it out.
using your calculator, so it might be rigged.
Let me drive it.
It's set to degrees.
192.7.
035.819.
And the angle
I got this.
was 15.9.
That's your feet.
That was good book. That's where I read it from.
Yeah.
Alright.
How'd you get 15.9?
How do you get the angle from that?
How'd you get 15.9?
I got 41.987.
I don't know. Took reactive component divided by the resistive component, arc change of that, and I may be wrong. Let's see, yeah, it probably is close to 4 degrees, now look at it.
16.
Yeah. Oh, let's see. Tangent minus 1. Alright. Right, let's see. It's 180. 10 Rex minus 240. Close that. Divide that by 200. 10 Rex. Try that again.
What's the formula, sir?
Reactive component divided by resistor.
I got it. I got it.
Square.
put up there?
15.9.
15.9.
Alright, now two. Put on this way.
Hey, girl.
See?
Yes, Tony.
Alright. Now, what you wanna do is you wanna add, you want the total impedance, you wanna add this plus this. Alright, well, this is in polar, and this is in rectangular, it's just one resistor. So what we need to do is we need to convert this to rectangular. Then we can add them directly. So, let your calculator do your work, or you can draw it out. Here's the impedance is 192.7 at 15 degrees. You can break that into the R and the Y, or the X and the Y. Or let your calculator do it. Alright. Let the calculator do it. I use the angle function. So I hit second function, PRB, that gives me the DMS, R to P, and I tab over and get the R to P. Alright, now I want to go from polar to rectangular, so I hit number 3. I want X component. Alright, so I put 192.7. Then hit second function period, which would be a comma. And then I punch in the 15.52. Hit enter. And I get 185. .67. That's the X component, or R component, however you want to look at it. Plus the rectangular component, I'll do the same thing, hit second function angle. Tab over to RP, and I'm gonna hit 4, because I wanna go find the Y component. Alright, punch in 192.7. Now hit second function period, get the comma, 15.52 again. Hit enter, I get 51.56. Alright, that's the Y component. Or, since it's positive, that's the X sub L component. So I got an R and X sub L. Or, but calculator doesn't know what you're dealing with. Calculator calls it X and Y. Alright, but it becomes R, and since it's positive, this is X sub L. Alright, so let's just leave it that way, R and X sub L. Alright, now that's in rectangular. So now it's easy to find the total impedance. Total impedance, simply this R plus 185.67 plus 51.56, alright? This is R, this is R, and this is X sub L. That's the total impedance in rectangular components. Alright. So we just, all we're gonna do is we're gonna add the R's, 51.5 expelled. There it is in rectangular components. While we're here, let's convert that to polar. This is rectangular. Now let's convert it to polar. Alright, that's gonna give us an angle and a magnitude again. We'll let the calculator do the job. Hit second function angle, tab over to R to P. Now we're going from rectangular to polar, so that's the first one. It's gonna give us the radius or magnitude. So we just hit enter, and then we punch in 185.6, I'm sorry, 285, excuse me. Second function angle, bring it polar, enter, that'll be 285.67. Second function period, which is comma. And then we put in the 51.5. Hit enter, and we get 290.3 roughly. 90.3. And it's gonna have an angle. We hit second function angle, rectangular polar again, you're gonna get 2. We punch into 285.67. Second function comma, and we punch into 51.5, hit enter, and we get 10.21. Alright. So we got an impedance of 285. .67 plus 51.5. That's in rectangular, or in polar, it's 290. Angle 10.2. So those are two ways to express total impedance. Alright. We got the parallel impedance right here. That was 185.67 at an angle of 51.9, or no, I'm sorry, 51.56, or that's the rectangular, or the polar, which is the 192.
I'm still gonna use your video.
0.7
It's just sort of like a
at
timeline.
an angle of
thing.
59.
Let's go for some timestamps in there too.
That's the parallel piece. Now, what is the voltage across the parallel piece? Okay, I'm sorry, I didn't give you, that's Z. We don't know ZP, that was just that was what? That was parallel piece, all right, Z parallel. Now, what's the voltage across that parallel part? Alright, should put over here. And it's VZ. Well, to do that, I want to use the voltage divider rule. Alright, I'm just simply going to say voltage across the parallel impedance is equal to source voltage times ZP over Z total. Alright, since I'm multiplying and dividing, I'm gonna leave it all in polar. Alright, so I'm just gonna substitute values for that. Alright, could be 120 times, alright, parallel part, 192.7. And it's at an angle of 15.5. The total impedance is 290. At an angle of 10.21. That will give me the voltage across parallel part. Alright. So 192.7 divided by 290 equals 0.66 times 120 gives me 79.74. And an angle of 15.5 minus 10.21. Alright. Now, that angle is real small. The reason it's small is because these being equal in parallel are supplying their own currents. They're not, the power supply doesn't even know they're out there hardly. Alright, so really and truly, all we got is 100 ohms and 200 ohms. Alright, because these two, being that they're supplying each other's current, there's very little difference between the two. Most of the voltage is just voltage divider here. That'd be 200, that'd be 120 times 200 over 100 plus 200. 300. Alright, if you do that, it should come out and be pretty close to 80 volts. Because there's not much phase angle difference. So 120 times 200 divided by 320, 300 equals 80 volts. Alright, so basically what's happened is these two have canceled each other out. Because they're almost equal in magnitude, not quite, but close. Alright. So as a result, most of the current, I mean, these are basically canceling each other out, so they don't even exist. They're like open circuit. Because there's no current going this way, because these two are supplying. So as far as this is concerned, it doesn't even see this. All it sees is that resistor. And you can tell that by looking at the phase angle. Phase angle is only 5 degrees. This impedance. Right? We only got 5-degree phase angle. That means everything's almost in phase. That means this ain't even there. That's why I get the 80 volt drop across here. So actually, when you do the calculation, it came out to be 80 what? 80 something. 79.74. So voltage right here, 79.74. Alright. Now what's the voltage you got across this resistor? It's about 40 volts. You got 80 here, 120 there. It's about 40 volts. Just round it off. got a 100 ohm resistor with 40 volts across it, how much current have you got? Four amps. Let's just see what we got across here. 80 volts divided by 200. How many amps you get there? 80 divided by 200. 2.5. 80.25. 80 volts divided by 200 ohms.
0.4.
No way, that's 2.5.
0.4.
You got 79, I'm just rounding off 80. Divided by 200.
0.4.
0.4, alright. 80 divided by 180.
0.4 repeating.
On what?
0.4 repeating.
0.4.
Yeah. 0.4444444.
Alright. And then 80 divided by 240. 0.333.
Yep.
Alright. Now, that's the currents. Let's just look at the currents for a second. Alright. We got 4 amps through the 200 ohm resistor. We got 0.44 through the inductor. We got 0.33 through the capacitor. Alright, so we subtract these two, that gives us 0.11. So we wind up with 0.11, and we got 0.4. What we want to do is find out what happens when you square this, square that, and take the square root. So the current here, this would be the source current, equals 0.4 squared plus 0.11 squared. We'll take square root of that. Four squared plus 0.11 squared equals second function square root second function answer equals 0.41. I'll say 0.415. Alright. And again, if you do this actual voltage minus that, it's gonna come out closer to 0.415. Because it's not quite 80, we were just kinda eyeballing it, guesstimate. So it makes sense. Alright. These two currents canceled each other out. So really the only current we got is coming mostly through the resistor. Anytime you get close to equal components from a reactive standpoint in parallel, they don't draw any current from the source. Right? Because these two currents are 180 degrees out of phase. When the current's going this way here, it's going that way. When this current's going this way, this current's going that way. It's almost the same current, going here, going there. When this current goes this way, this current's going that way. So all they do is share current back and forth, back and forth, back and forth, back and forth. it's like they ain't even there. All the current from the source is just flowing through resistors. What little bit flows over here is just enough to keep the circulation going back. That's why that swing set. Once I get it going, all I need to do is just lightly push it, and the swing will keep going. Right? Takes a little effort to get it going. So when you first turn this circuit on, yeah, you get a lot of current going, charging here and here. But once these two start sharing the current, they don't draw it from the source anymore. So when you get these two components equal or close to equal, they don't draw any current from the source.
Oh, yeah.
So it's like they're not even there. It's mostly a resistive circuit. If I made them equal, you wouldn't even need to do a calculation. You just sit here and say, oh, they're equal. There you go. That's all I gotta worry about. Now, there's still current flowing in them. They still have the same voltage across them. But the fact that they're out of phase with each other, one's applying while the other was using it up, vice versa. Alright? So the source doesn't even look at them anymore. Only time it looks at them is when you first turn it on. It says, whoa, they both want current. I'll give it to them. Alright, I'll get the capacitor current first. Then once I give it, I'll let the inductor draw a little bit. But now I'm gonna let them both supply their own current. So I don't need to. So in that respect, you can guesstimate and not be too far off. Because they were so close to being together, you say, boom, these two cancel, you left me with a resistive circuit. For the most part. And you wouldn't have been too far off. Now, when they get out of whack, yeah, the inductor's only gonna use up a little bit of that capacitive current. So where it's coming from? It's coming from the source, or vice versa. If the inductor is real small and the capacitor is real small, drawing a little bit of current, and the inductor is large, then opposite's true. Right? You got a lot of inductive current, but not much capacitive current. So it's gonna draw its current from the source. It's when the two are equal that they supply each other's current. It's a little confusing to look at the results and say, well, doggone, I know I got capacitive current, I got inductive current, how come I'm not drawing any more from the source? Because the two are supplying each other. Any questions?
So once you found VP, you took it and just subtracted that from the total voltage, and then that's what you had.
Yeah, I mean, it has the voltage here. You got the voltage here.
Yeah.
Subtract those two.
And you got the voltage across the resistance.
Gives you voltage across here.
Okay, that's what I thought.
Now, got it.
And then you find the rest of the stuff out easy enough from there. Okay, cool. That's all I need to know. Thank you, sir.
Or you go back, once you had the circuit current, and you just multiply circuit current by 10.4 amps, times 100 gives you 40 volts. Either way.
Appreciate it.
Is that all that's gonna be on the test?
Hmm?
Is that all that's gonna be on the test? Alright.
You better know the charge on electron.
Positive.
You better know what we measure potential it with, in,
Huh?
electrical potentials.
Which is?
What we measure electrical potential with. Or in, what units? Volts.
Yeah.
Volts.
Electrical
Negative
potential.
volts.
Where we,
So
where we
we're, it's
measure
such a weird way.
resistance in.
Sorry?
Where we measure resistance in.
Ohms.
Ohms. Where we measure current in.
Amps.
Amps.
Okay.
Don't mess them up.
Too late.
What was the first one? The one with volts?
That is such a weird way to put it. Potential.
Electrical potential, what do you measure? Electrical potential in. Electrical pressure. Volts. Y'all have a good day.
Yes, sir.